nice introduction, and also for the invitation to be here. It's a lot of known faces already, and I look forward to also get to know many more of you in that conference. Today I'm going to talk about our recent work on visualizing Majorana zero modes in topologically detected edge channels, specifically Bismuth. We already heard about some things about Bismuth from Raquel, and I hope the speaker after me, Malek, will also tell more stories about this wonderful material. So what I'm presenting today has mostly been done by me and Yonglong, who was a grad student in Ali's lab until 2 days ago. He now graduated and has a better life. And Sangjun, who's a postdoc, and also by Andre, here, and Jian, who's a professor himself now in China. So the perspective of topologically protected quantum computation in using Majorana zero modes has ignited a lot of research in that direction. And for a couple of years now, a lot of different platforms have been explored, perhaps most notably semiconducting nanowires developed in Delft, but also now spearheaded in Copenhagen, where people look at those nanowires in the presence of proximity-induced superconductivity and external magnetic fields to find so-called Majorana zero mode at 0 bytes. And there's been a lot of work on that, and I think this field was moving fast for quite a while. Also because there's a second platform existing, the so-called ferromagnetic iron chains of iron sitting on the lead surface, where also Majorana zero modes can be found as end states of the system. And these two platforms have been very valuable in terms of understanding some aspects of Majoranas in condensed matter systems so far. For the past couple of years, also a number of new platforms surfaced, which all by themselves are very exciting. And I think it's not wrong to say that the field has, in some sense, consolidated now and kind of diversifies in terms of the platforms, also striving to move ahead of just saying, well, there's a zero bias peak, but more towards how can we manipulate Majorana zero modes in terms of the spatial location, in the idea of being able to, at some point, perform these braiding operations. In that spirit, what I'm going to talk about today is a Majorana zero mode platform. It's in fact the oldest platform proposed, which is based on the helical edge states of topological insulators. So as most of you know, if you have a 2D TI, it will be encircled by a nice pair of helical states running around the perimeter. And so what is very beautiful about this platform is that as soon as you introduce proximity-induced superconductivity into these states, you realize naturally a topological superconductor. And so the important aspect now was found by Liang Fu and Charles Kane about 10 years ago, that if you are able to realize a segment that has a trivial gap, for instance by coupling the edge state to a magnetic insulator, you can in fact realize a topological mass domain wall between a region of a non-trivial gap, which here is the superconductor, and a trivial gap, which is the Zeeman gap. And right at this interface, you can localize a fermionic mode, which for our system running Majorana zero mode. So the platform we have been realizing this proposal of the past couple of years is Bismuth. You've already heard about it, and I think importantly it was found about a year ago that Bismuth is perhaps the first example of a higher order topological insulator. And as we've already seen, instead of just having a, let's say, 1D edge state running around a 2D TI bulk, for a 3D bulk, the edge state is going to run around the hinges. And there has been now this joint paper by Princeton Strick and also people in Paris where one could see that both the theory and also experiments line up very nicely in terms of finding such an edge state on every other edge on the surface of Bismuth 111. To realize the Fu and Kane model, what we have been doing now is growing thin films of Bismuth 111 on top of niobium, which is a bulk superconductor, and which we want to use to introduce proximity-induced superconductivity into the hinge states. So what you can see here is a topography which was recorded by means of scanning tunneling microscopy. Just as a brief introduction, because you're going to see much more STM data today, which is great. What happens here is you have a metallic needle-like tip scanning all along the surface, and you basically capitalize on the quantum mechanical tunnel effect to get a sense of the distance between your tip and sample. And as you scan around, you can basically resolve the atomic scale topography of the sample, and this is how this picture was done. And what you can see here now, importantly, is that bismuth grows in very nice flat terraces on top of the superconductor, and also grows, as you can see here, by this triangular arrangement in a 1-1-1 phase, which is the phase we need to perform our experiment. What is very beautiful about STM is also that it allows to study the local density of states of your system by means of its density of states. And what you can do is you can apply a bias voltage between your tip and your sample, which basically gives you a handle on the energy of the system. And so when you study now basically the differential conductance of your tunnel junction as a function of this bias voltage, you can access the energy result local density of states, which is very powerful. And when you run such an experiment now on our beautiful bismuth sample, and let's say put your tip on one of those edges, which we now call A edge, you can in fact see the emergence of a very localized P, which is very typical from one-dimensional edge state. And if you now move your tip further to the second edge, which is not supposed to have an edge state, you can see that this is more kind of like a broadened spectrum without this very dominant peak. And so this is very consistent with the previous study I've been talking about, and also basically the first discovery of those topological edge states in bismuth by our group about 5 years ago. Now the important part comes here, that we can also visualize the 1D character of this state, but basically mapping out this local density of states as a function of the spatial position of the STM tip. And as you can see, every second edge here basically lights up a nice red, very comparable to what you've seen before. Importantly now to realize the K model here is not only to have a hinge state, but to make it superconducting. And so what I show you here now is another experiment where we basically zoom in onto such an A edge and take a spectroscopic line cut along the edge. What we do here is we move the tip along the edge and record the differential tunnel conductance as a function of the tip position and the applied bias voltage or energy. And so what you can see here now is a very nice particle in a box behavior of a 1D system, which basically illustrates this nice 1D character of our band structure of the edge state. And importantly, if you look closer at energy, you can see the evolution of a very sharp gap cutting right through the lower kind of pocket of this 1D edge state. You can also now take a vertical line cut here and plot it as a function of the energy. And as you can see, we can extract a very nice superconducting gap that can even describe by means of BCS theory. And what is very important here is that we find that the gap we extract on the hinge state is approximately of the same size as that we can find on the bare niobium substrate, which illustrates that the proximity effect into the hinge state is very, very strong. Lastly, what is missing to making Majorana is like a cooking recipe, right? You need a few ingredients put together and have a nice dish. So for us to make it very tasty, we need magnetism. And the way we get this is basically a bit kind of supported by our instrumentation in the way that we can evaporate in our environment individual magnetic atoms onto the surface. And by applying a little thermal heat, the atoms start to walk around and form clusters. And for us, luckily, those clusters tend to adsorb at the interface between A and B edge, where they naturally adsorb at places where they can basically induce those magnetic gaps into the hinge state. If we zoom into that system, we can see now a typical cluster shown here. They typically, as I said, sit at the end of this A-B edge corner and are a few angstroms high. What we're doing now to characterize these clusters and make sure they're actually magnetic is to perform spin-polarized STM experiments. And the way this works is that you use a magnetic STM tip and now study the tunnel conductance between your tip and your sample. And because of the so-called tunnel magnetoresistance, you can basically distinguish cases between where the tip and the sample magnetization are aligned versus the case where they are anti-aligned, because this will give you a different conductance, which is a measurable effect. So what we have been doing now is to put our STM tip here right on top of the iron cluster and study the conductance through our tunnel junction as a function of the applied magnetic field. And as we sweep the field back and forth, we can observe a very sharp step-like feature around zero field. And without going too much into detail, the important message I want to convey here is that such a feature is very typical for tunneling between a ferromagnet and, in our case, a superparamagnetic tip. Interestingly, as we move our tip along the edge a bit away from this iron cluster, we can still see this kind of step feature, even though of a reduced magnitude. And if you now plot the relative height of the step feature as a function of distance, we can actually find a very nice oscillatory decaying behavior consistent with an 1D RKY-induced spin polarization into our edge state. So having now shown that our magnetic clusters are indeed ferromagnetic, we can also characterize the magnetism in more detail. And what we use here is the super paramagnetic property of our SDM tip that we can now tilt basically in any direction of space by using a vector magnetic field. And what I'll show you here now is, for instance, an example where we tilt the SDM polarization along the edge, which is the x direction, in like plus x and minus x, and in each case record the height, which is different because of the tunnel effect, the magneto-tunnel effect I was talking about. We can now basically do this for all three directions, x, y, z, and use that to reconstruct the magnetization vector of our iron clusters. And we have done this for a different number of clusters, and what we have found is that all of them are ferromagnetic, however, with a different distribution of magnetic amplitudes. And this will have big ramifications later. Now, now that we have cooked our dish, let's see how it tastes. And so basically here we see now an iron cluster, zooming onto such an iron cluster at an A edge end, and we want to look now whether indeed this interfacial zero bias peak exists right at the interface between the superconducting hinge state and this ferromagnetic cluster. And what you can see here now is the result of a spectroscopic line cut taken along the white dashed line. And while our SDM tip is sitting on the hinge state, we can see a well-developed superconducting gap, but as soon as we approach the interface of the cluster hinge state of the hinge state with the cluster, we can indeed observe the evolution of a very sharp zero bias peak, as you would expect for the system. And now as we move on to the cluster, maybe it's best seen here, zero bias peak basically vanishes and a pair of finite energy states, so-called Shiba states, emerge. Those Shiba states are very typical for systems where basically magnetic moments interact with a superconducting condensate. Just as a background information here. To confirm the localized character of the zero bias peak, we can also now plot the zero bias conductance along this line, which is shown here in red. And as you can see, the zero bias conductance really peaks right at the interface in a kind of localized way between the iron cluster and the hinge state.
How
Yes.
many atoms are in this iron island?
So usually those islands are between 3 and 5 nanometers long. We can't really resolve the atomic structure. It's just because I guess the sitting too closely packed, given the orbital structure they have. So
if you then, so then you say you move from blue to green to red. So this means how many atoms are you? So what's the atomic distance of this?
So here's the atom length.
So this should be one atom apart, or?
Well, I mean, it's hard for us to tell the atomic lattices for the iron cluster, but for instance, bismuth is about 4.5 angstrom. So if you take this as a length kind of a system, you can see that perhaps here we look at this at like 5 to 10 unit cells or something. The observation we've made here now we can also confirm by means of setting up a very simple tight binding model of our system, where we basically look at a individual bismuth bilayer coupled to a ferromagnetic cluster in the presence of proximity-induced superconductivity. And then we can solve for the eigenstates of the system and calculate the result of an SDM experiment that you would take when your tip moves all along the hinge state of such an A and B edge. The result is shown here. Now. There we go. Okay. The result is shown here. So when your tip, let's say, is far away from the interface on the A edge, you can see, in fact, the existence of a nice superconducting gap. And as you move to the interface, also the calculations here show this nicely localized zero bias peak, whereas on the cluster itself, you find this so-called finite energy Shiba state. So this matches all very nicely our measurements. And what is also interesting here is that the second interface we do not observe in the calculations the zero bias peak. It's just kind of a smeared out feature around zero bias. And for a reason that is kind of obvious, because the the hinge state, as it basically dives down at this AB corner into the bulk, hybridizes with the bulk states of bismuth. And for that reason, it basically leaves very little spectral weight localized on the edge. And since the Majorana zero mode itself emerges out of the normal density of states, also the Majorana zero mode will localize with only very little spectral weight at this interface. And this is actually something we can confirm by our experiments. Here's like another cluster at an A kinky edge interface. And while the upper end, as we've seen before, shows zero bias peak, the lower end does not. It just basically shows a finite gap filling. You can now basically subtract this gap filling from the superconducting gap to get a sense of the spectral character of this gap filling. It's just basically purple minus white. And what we can see is that this kind of additional gap filling we observe here is somewhat reminiscent of what the theory kind of tells you for such a broadened out state. So with this and many other experiments, we have confirmed that the zero bias peak is a very robust feature indeed for us to observe in our experiment. We've done a lot of sanity checks to exclude that this is just an accidental zero bias peak. But the question is, how can we actually provide evidence that this is a Majorana zero mode and not just any other trivial zero bias feature? And so a way to do this with STM is very neat in the way that we can study the spin properties of these states and use them as a litmus test for the non-trivial character of these states. And the way this goes is, it actually goes back to previous work on the iron chain platform where this approach has been developed. And the way this goes is that Shiba states by themselves usually have a spin polarization which is asymmetric about zero energy. That means that a Shiba state at positive energy will have the opposite spin contrast of its partner at negative energy. And so if you now move to Shiba states basically to zero energy, obviously they're going to overlap to form a trivial zero mode, but the spin contrast cancels. This means, on the other hand, that if you observe a zero bias peak with a finite spin contrast, this immediately gives you experimental evidence that's non-trivial in nature. And what we have done now here is first to measure the spin contrast of a Shiba state on top of the cluster, which is shown here. And as you can see, it shows the somewhat asymmetric behavior I've been just describing. However, now if we go to the interface of the hinge state with the iron cluster where the zero bias peak exists, you can see that doing a measurement with a spin up polarized tip and a spin down polarized tip indeed shows a strong difference, which manifests in a large spin contrast of about 12%. And this basically is direct evidence that this is in fact a Majorana zero mode and not just some coincidental zero bias peak. What is also very important to note here is that the electron-like Shiba state has opposite spin contrast compared to the Majorana zero mode, like negative to positive, which means they have to point along different directions in space in terms of a spin component. And this is also consistent with simple toy model calculations, where you find that in the most simple assumption, usually the Shiba state, which follows the magnetism, will point in a direction orthogonal to the Majorana zero mode. Okay, ultimately we still were finding clusters that did not show a zero bias peak, which was very puzzling because we thought, well, here we have a really nice story to tell, but still it's not consistent because some of the clusters do not show a zero bias peak. And so this was puzzling for the first moment because we realized they all look the same, but still 25% do not show. Interestingly, what we found, however, how much time I have? 8 minutes. Okay, I'm really fast now. Wow. What was interesting now to see, however, is that you can actually correlate the existence and absence of such zero bias peaks with the type of magnetism we observe on these clusters. And this is shown here. This is now again the plot you've seen before. And it is very interesting to note now that only the clusters that basically have a suppressed magnetization component in MY direction, which if we relate this to our system here is the component in plane perpendicular to the edge, only these clusters do show a zero mode. Whereas the other ones, which have equal component in all three space directions, do not show a zero bias peak. And while this observation in the first moment may seem unintuitive, it actually makes sense if we compare the different effects of the spin polarization of the cluster onto the edge state. So now for simplicity, let's assume we have a topological edge of bismuth, let's say described here in color by the UL model for bismuth, and couple it to a set of parabolic bands that are spin polarized. If you now switch on a finite coupling and assume the polarization of these spin polarized states to point along the x direction, which is in our case along the edge, you do indeed see the opening of a very nice hybridization gap. Don't be confused by these little dots in the gap. This is basically spectral weight sitting on the iron itself. So this is what you see here, like in point size and color, is basically the spectral weight of the hinge state, whereas what remains here is basically the spectral weight from the iron states in the calculation. So the bottom line here is using an X polarization cluster gives you a nice hybridization gap. If you now add a second component to your cluster magnetization pointing in the my direction, you just add something to it, you can now see that basically, because of this non-orthogonality, you start to tilt your band structure due to this coupling in some non-trivial ways, which eventually does not open a gap as you would require to realize this mass domain wall inside your edge state. And this is now giving us some sort of very consistent picture between what you observe and between what you can describe in terms of a simple toy model. And with this, I'm at the end, and I think this is a very neat aspect about this platform. You can actually use magnetism to switch Majoranas on and off. And we think that this may be interesting also to move ahead, for instance, by engineering little iron clusters that have now very weak magnetic anisotropy, so that you can use, let's say, external magnetic fields, for instance, to switch the magnetism and then get some, actual control handle on the existence of Majorana zero modes. I think that's one direction we want to pursue, but I think what is even nicer about this entire Bismuth platform, I think I want to highlight this here very carefully, is that this is not a pure SDM platform like, you have perhaps seen previously on the iron chain platform, which is a pure SDM experiment, right? But Bismuth here has already been found to be integrated, shown here in brown color, as nanowires into transport experiments. And this actually goes back also to the last year paper of the higher order topology, which was partially in collaboration with the people from Paris doing these device type of experiments. And I think this is a very interesting thing to mention here, and direction to go, that now this, what we have done here, can actually be translated into a device type of platform where you can basically try to manipulate those Majorana zero modes in more device geometry, giving you usually some more control on these knobs. And then you can think ahead and, consider potential experiments like the Majorana hexagon and others that have been proposed to actually get beyond just seeing a Majorana, but actually doing something with that. And because of that, I'm a big fan of Bismuth. And
Attention, please. This is your building fire life safety director. We're conducting a test of the building's alarm system. Please disregard any alarms that you may hear or see. This is only a test. Once again, we're conducting a test of the building's fire alarm system. Please disregard any and all alarms that you may hear or see. This is only a test.
Sorry about that.
Anyway, so again, let me just repeat this. I think Bismuth, we have seen from Raquel, is really cool. I hope this convinced you as well that there's cool stuff happening with Bismuth, and I can see a lot of more things going to happen if people continue these experiments and hopefully find more Majorana physics. In Bismuth nanowires, and with them at the end, and thank you for your attention.
Any questions? Yeah, congratulations, very impressive data set. I have two questions. So the first one was about the induced superconducting gap. So how come that it's the same size as the superconductor? Can you expect that you have some sort of
so this is very
induced gap?
Yeah, this is very not intuitive. You would think that it's because of the proximity effect, it would rather be like soft. What people mean by saying it's kind of like not going to zero and has some kind of rounded shape.
Maybe at least smaller.
Yeah, so, I like to speculate and always argue things I'm getting ahead of myself when I say this is because of it being a hinge state, because, it goes down to the bulk, and because it's a very thin film of perhaps only, in our case, 20 to 30 angstrom, depending on how thick we grow. It basically, it's a 2 nanometer system. If your hinge state has a spatial extent of a nanometer, you can easily think how well it couples to the underlying niobium. But I don't have any proof for that, it's more like speculation. Other than that, usually you can say, well, proximity effect strongly depends on the Fermi surfaces of your participating materials. And in that case, you can say, well, you have apparently a good match between your hinge state Fermi surface and the underlying niobium. But since we don't have a good idea about the band structure of bismuth by itself, it's hard to get quantitative on that end.
Second question is about the energetics of the edge states. So in the previous slides, I think you showed that they are in the unoccupied states, right?
Yeah.
Does that matter for anything?
Absolutely. That's something which I did not highlight, but it's a very good point you mentioned, because when you think about proximity effect, you mean pairing, superconducting pairing in a state, you need charges to do that, right? This state I've been highlighting here is basically the highest energy hole pocket of this edge state, way above Fermi energy. So obviously in this state, there's no charges to be paired. So what you need is basically parts of the edge state band structure that exist across Fermi and also cross Fermi energy, right? Only in that case you can actually pair charges in the edge state. And so this is in fact the case here. So these features you see here, I don't have the data right now, but I can show you later. We have more data here basically showing that this is some sort of hole type pocket. And here we have an electron type pocket, which is obvious from the next slide here, right? So you can see this kind of particle box-like behavior with an onset at -8 millivolts, which basically crosses Fermi energy and then matches the requirement of having an occupied state to be paired. But you can see it's a very narrow window, so it's
Okay, so regarding the magnetization dependence of your zero style speed, can I naively understand it as that you have a preferred access for your spin in your helical hinge states? If so, what determines that?
Right. I mean, I guess depending on some more let's say more complex spin textures, it can be a bit more involved. But generally, when you have a time reversal symmetric helical state, you'll usually have some spin component pointing in the out of plane direction, which in our case is like ZY plane if X is pointing along the edge. So this is also something which you can see from our type binding calculations. So and maybe to add to that, so what you in fact need in the ideal scenario is a magnet which only points along the edge, because then you would have the situation that it's purely orthogonal to the spin of your hinge state and would immediately gap it out entirely. Whereas a magnet which points in the plane of this hinge state would not gap it, obviously. These are the two limits, and obviously this is what you would achieve in experiments, but it's hard. I mean, I'm not necessarily sure whether there's like magnets in a realistic scenario that you can tune between, let's say, an easy axis as it grows and a more harder axis as you try to apply a magnetic field or something. So
Probably control the shape of your cluster.
right. I guess. So if the cluster is turning smaller, I can imagine it's easier to rotate the magnetism. Say you have a long kind of sausage thing sitting on your edge. I can't see a way of tuning that magnetism personally.
So,
You and that, Philip.
so in the maps that you have with
Like this?
exactly like that, with a lot of density of states at these A edges, but not at the B edges. Did you ever try to gate and then or just look at a different energy and see if this difference is this contrast maintains, or is there any point that the B edge also starts having some spectral weight?
Yeah, so I think part of the answer is
It's in that picture.
in that picture, though my laser pointer is giving out a bit. Yeah. So as you can see, I think what I want to highlight here is these features again in that feature, which basically are the van Hoff singularities of the 1D stage one on the A edge. And you can see those are all kind of like smeared out and absent. So in that sense, as you can see here, the local density of states on the B edge is mostly much weaker than on the A edge. And this feature here existing at about 230 millivolts is actually the decaying surface state. So you could think there is potential maybe shifting this peak to some different energy, but so far we have not found that. And as you can see from here, there is not any obvious feature that would basically shift the spectral weight away. It rather seems it's completely suppressed.
Yeah, so I was always quite interested in these results. My question would be, why do you not see something at the B edge? Because if I think of these pictures that people draw, these continuous things snaking around. So is the statement then that the bottom corner somewhat hybridizes with the bulk, or why is there?
Getting into drifting sand now. like ongoing discussions like about the about what the hinge state does as it reaches its corner, and the initial picture perhaps from the Nature Physics paper of last year was that it kind of goes down and somewhat into the bulk and comes up again, but obviously this is like trivializing the situation. So
but it's an important topological question whether or not it forms a continuous object or not.
right, I'm an experimentalist. I live with what I observe.
Bismuth has a surface state also,
Yeah.
which is trivial.
Yeah.
You can't get rid of
Yeah.
for reasons that I can't go into, but it's there. So if that thing goes down, it's going to hit the surface state.
Yeah.
And you can see it in the experiment.
Yeah.
But it's also hitting the surface state on top. It's the same surface.
That's right. It's a bit separated on the surface on the one of the. And then it goes down. It's
Yeah, maybe one last question.
So the other end of the iron droplet is, so what happens there? So not sure what happens.
So, I mean, it probably connects to Philip's question that, like, what does the hinge state do at this corner? And so I think there's two answers to that. First, it dives down and it delocalizes. That's our understanding. That's also why you don't see it on the B edge, even though you could expect, let's say, it just lives on this 2D island. It would live because of inversion symmetry on the B edge, let's say on the lower end, you would think there's more spectral weight. We don't see that, which is why I think it really strongly hybridizes with the underlying states. And B, we can manipulate the position of these iron droplets.
Yeah.
So ideal scenario we dream of is that these guys start to cluster right on top of an A edge so that there will be two Majoranas left and right. Since we grow these clusters self-assembly, we don't have control. We try to move them around, it hasn't worked yet. But certainly a way to go in the future, which is something we're also going to try, is to grow them with perhaps an optimized parameter set so as to find them on the
Yeah. So there must be like some other Majorana state, but you're saying it's kind of diving in and it's not localized on the surface? Is
Yeah,
that
just
what's
yeah, exactly. So just think about the Majorana kind of emerging out of the band weight of the hinge state, right? And if the band of the hinge band delocalizes into the bulk because of hybridization, basically you have for that reason little spectral weight to kind of construct a Majorana out of it. It certainly has to be there because you have one, so the other half has to live somewhere.
Yeah.
It's just we don't pick up the
It
weight.
becomes delocalized. Okay.
Yes, it's somewhat not localized. I wouldn't say it's delocalized in terms of like overlapping with the other one. It's
Hopefully
not
not,
it's not localized in the
Yeah.
way that you don't have the normal density of state weight to be localized.
So you can't.
Yeah.
You want to set up and maybe we have one more short question or something? Philip again.
Well, if there's
Yes.
if there's time.
Go for it.
So what is then the meaning, or what is the importance of this being a thin film in terms of subband quantization? Is that relevant or not? Or could you do the same thing on bulk bismuth in principle? I mean, you need the superconductivity, I understand, but
That's a very good point. Like I think generally bismuth has the complexity that if you grow it too thin in terms of like going below some 30 nanometers, it develops quantum well states. In this very thin film limit, we haven't observed that, obviously, which is perhaps surprising. But I can imagine that if you look at nano wires living in this kind of 30 nanometer range, you actually have to consider these effects more obviously. But in our case, it's simply matching very well what you see on bulk, and we don't see any transition.
but then your bulk it's a semi-metal, right? It's not an insulated.
Yes, exactly. So that's very important here. Bismuth by itself, even in a 3D version, right, it's semi-metal.
That's right.
And that's actually important to the nanowire experiment I was highlighting, because there you can actually, and it has been done by the Paris group, you can realize a situation where you end up with a basically insulating bulk because of these quantization effects for small enough bulk thicknesses, whereas having still conducting hinge states. And this is like the ideal scenario, right? You only have the hinge states.
It's also strange because their nanowires are 100 to 200 nanometers wide, right? So there's a question how that actually works.
I guess you can optimize it certainly, but they still, like the analysis of the data seems to suggest that the bulk transport is strongly suppressed, right? And
That's probably more for scattering reasons than for subband quantization.
perhaps, yeah. But let's put it this way: the perspective is there that you can realize this platform on a nanowire base with an insulating bulk. And
Fascinating. The only question was whether or not subband quantization is important to what you see or not.
no, absolutely not. We don't see any of that.
It's also strange.
Right. But I guess it depends on, if you like in the 2D limit and think about it more from a bilayer perspective, I guess you don't run to the 3D limit where like the quantization of the CX is actually relevant, right?
Mm-hmm.
Because it's much thinner than any of the Fermi wavelengths will be, right?
Yeah. Cool. Okay.